In this video, we will be going over the conditional probability worksheet and how to solve it. If you look up at the top, we have that P, A, B. The way that you would read that is the probability of A given B. And there is that formula up there at the top that we see right here. Now, we can use that formula, but I'm going to show you something else that we can do specifically for question number 1. For question number 1, it tells us that we have a bag with marbles. 3 of them are blue, 2 of them are red, and 5 of them are green. So that means total, we have 3 plus 2 plus 5, which gives us 10 different marbles. If you look at subsection 1, it says the probability if my second draw is blue and my first draw is red. Now, if your first draw was red, that means one of these reds comes out of the bag. It's no longer in there. What we're left with is 1, 2, 3, 4, 5, 6, 7, 8, 9 marbles. We took 1 away, so 10 minus 1 is 9. My total, which is going to be the bottom of my fraction, is going to be 9. Now, it wants us to say that the second draw is blue, so I just have to figure out how many blues are left. Taking a red out does not affect how many blues are in the bag, so I still have 3 blue marbles. My simplified fraction is going to give me 3 divided by 9 simplifies down to 1/3. Now let's do something similar for question number 2, subsection 2. It tells us that the probability, we're trying to find the probability of if the second draw is blue, given that the first draw is blue. So if my first draw is blue, that means one of these blues comes out here, it's no longer in the bag. And as we mentioned earlier, the total is going to go from 10 to 9. 9 is going to be in the bottom of my fraction. That's my new total. We just have to figure out what's in the top. So if I pull 1 blue out, there's only 1, 2 blues left in the bag. So we have a 2 on top. And 2/9 is already simplified, so I'm going to write it down in my answer box. 2 divided by 9. So section 3 here is a little bit different because we do have 3 draws, but we're going to treat it just the same. Our first draw is red. So one of these reds comes out, it's no longer there. That's a red. Then we have a blue is pulled out. So we're going to take one of these blues, it's going to come out. That one is blue. I've pulled 2 marbles. That means my total is no longer 10 and it's not even 9. My total is 8. So at the denominator of my fraction, I'm going to put an 8. We just have to figure out what goes on top. So I'm pulling another blue. I've already pulled 1 blue out, so I don't have 3 blue marbles anymore. I only have 2. When I simplify this fraction, my reduced fraction is 1/4. For this last one, it does give you a hint by drawing arrows to the fact that this says the first draw is blue when it also says given that the first draw is red. You can't have 2 first draws. So if my first draw is blue, my first draw cannot also be red. This is not possible, so the probability of this happening is 0. For question number 2, instead of looking at marbles in a bag, now we're looking at cards. So we're drawing 1 card from a standard deck. When we're given this probability of a queen given a face card, I'm going to rewrite this with our equation from the top of the paper. We have our probability of a queen and face card divided by the probability of a face card. So when I'm doing this, I first need to decipher what is a face card. A face card is going to be anything that shows the picture of someone's face, which are the 12 cards that we see on the right-hand side here. There are a total of 52 cards in this deck. So in our denominator, we have 12 out of 52. How many of those face cards are queens? Because if it's a queen and a face card, we know the face cards. We just have to figure out how many of them are queens. Well, queens have the little Q, so it's just this middle bit. It's only those 4 cards. But the probability of that has to be from the entire total. So we have 4 out of all of the cards. So the probability of something being a queen and a face card is the same probability of just pulling a queen. When we simplify this, those two 52s are going to cancel. We're going to have 4 out of 12, which can be simplified one more time, and our reduced fraction is 1/3. So let's move on to the next question. What is the probability that a card is an ace given that it is a lettered card? So let's set up the same sort of equation. We have the probability of an ace and a letter card divided by the probability that it is a letter card. First, we need to figure out, well, what is a letter card? A letter card is anything where you see a letter instead of a number. So over here, we have our aces that have an A. And way over here, we have those face cards we saw earlier. They're all still letter cards because we see a J, a Q, and a K. So total, we have 16 letter cards, which means our denominator will be 16 over 52. So now we need to figure out, if we already know they're letter cards, which is what we just circled, how many of those are aces? And when you look here, aces are just the 4 cards on the left-hand side. So just like a queen is a face card, so that's just the probability of pulling a queen. An ace is a letter card, so it's just the probability of pulling an ace, which in this case is, it is 4 out of 52, not 5 out of 52. I got excited about the 52. When we start to simplify this, we're going to get 4 out of 16 because those 52s are going to cancel. And when we simplify that one more time for a fully reduced fraction, we get 1/4. For the third question, we're given the probability of a heart with a number card given that it is a red card. So we're going to set this up again, where we have the probability of a heart with a number, and it's a red card, divided by the probability that it is red. So we want to start off with the probability that something is a red card. My red cards are shown in the middle. All of these cards in the middle are red cards. That is half of the cards in the deck. Half of 52 is going to give me 26. So my denominator here is 26 out of 52. Now I have to figure out how many of those are hearts with a number. So not only hearts, but they also have a number. Well, by looking at this, I can see that my hearts are this second row here in the reds. But not all of them have numbers. The ones that specifically have a number are 2 through 10. Ace, Jack, Queen, King do not have numbers. So I'm only looking at 2, 3, 4, 5, 6, 7, 8, 9, and 10. I have 9 different numbers. So I'm going to set up 9 divided by, oops, I'm sorry, not 2, but 52. When I simplify this, I will get 9 divided by 26. Now, there's another way that we could do this. Instead of setting it up in the fraction divided by a fraction, we can just say, well, we have 9 cards that are hearts with a number, and we have 26 red cards. So we can set up 9 divided by 26. Those 52s are going to cancel anyways, so we don't necessarily have to show them. So let's look at the fourth problem, the probability that you draw a card with a letter given that it is a king. So when I rewrite this, we have probability that it's a card with a letter and it's a king divided by the probability that it's a king. So I'm trying to figure out how many of my cards are kings. Sorry guys, I typically erase the cards before I start the next problem. So now we're trying to figure out how many of the cards are kings. So we look over here on the right hand side and we notice that, well, 4 cards are kings. This means in our denominator we can write 4 over 52, or because based off what we said earlier, we can just write that our denominator there will be 4. We also need to figure out for the top, what about cards with a letter? How many different cards are there with a letter? And not only that, but how many of them are kings? Well, kings are considered letter cards. So just like how a queen is considered a face card, a king is considered a letter card because it has the letter K. So the probability for the top of this fraction is going to be the exact same. Well, if they're lettered and they're a king, it's still going to be this 4. We can write 4 over 52, or we can just write 4. 4 divided by 4 gives us a probability of 1. So if we're trying to draw a card with a letter, given that it's a king, it's going to happen every single time. It has a 100% probability rate. Let's look at question 5. We have the probability that a number is less than 6 given that it is a face card. So face cards have faces on them. There are these numbers over here, Jack, Queen, King. These are the highest cards you can have, although some people say that the ace is the highest card, but we're looking for a number less than 6. The numbers less than 6 are going to be on the left-hand side of this blue line that I've drawn. Jack, Queen, and King are not less than 6. So we don't even have to do any math for this one. We can say this is not possible. You cannot have a face card that is less than 6. So that probability is just 0. And for our last one here, we have the probability that an odd number is pulled given that you're pulling a numbered card. So let's think about what our given is. Probability of an odd and numbered divided by the probability that it's numbered. So I need to know my denominator, how many numbered cards there are. The numbered cards actually have numbers on them. So that's 2 all the way up through 10. We do not include Jack, Queen, King, and we do not include ace. Those have letters, not numbers. The total number of cards that I have blocked out in my square there, or my rectangle there, is 36. We have 4 rows of 9. So we're going to write 36 in the denominator here. And you can write 36 divided by 52, But as we mentioned earlier, that 52 is not necessary at this point. I also want to figure out how many of those that I've blocked off are odd numbers. So when we're looking at this, 2 is even. I'm not going to look at that. But 3 is odd, so I'll block that off. 4 is even. I'm not going to block that off. But 5 is odd. I'm going to block that off. 6 is even. 7 is odd. 8 is even. 9 is odd. And 10 is even. I have blocked off 1, 2, 3, 4 different columns, each with 4 cards in it. So I blocked off a total of 16 cards. And you can write 16 out of 52, but you really don't have to. Make sure that we write it as a fraction. And when we simplify this, 16 divided by 36, they're both divisible by 4. We get 4 over 9. Now we're on to question number 3. It's telling us to look at this table that's off to the right about the statistics at Phoenix High School. Part A is asking us, what is the probability that someone is full-time given that they're a male? Well, let's think back to our formula that we had. We have the probability. I'm going to write the word for A a little bit lower down here so I have some space. The probability that someone is full-time given their male can be rewritten as the probability that someone is full-time and they are male divided by the probability that they are male. So to do this, we have to look at our chart. The probability that someone is full-time and male, we have to look at where they intersect. So this is full-time. This is male. They intersect at 12. So the probability that someone is full-time and male is 12. The denominator says the probability that someone is male. So all we're looking at is this total here. Out of all the men, we have 28 total. So my denominator is going to be 28. And when I set this up as a fraction, I can simplify that down, and that's going to give me 3/7. Let's look at part B, which is asking a very similar thing, but with a different order. What is the probability that someone is male given that they're full-time? So how does this change our problem? Well, when we rewrite it, it's not really going to change anything about the top. We have the probability that someone is male and full-time, but the denominator is going to change. We have the probability that someone is full-time. So if we look at the chart, full-time male still intersects in the same place, still intersects at 12. But our new total that we're going to be looking at is the total number of people that are full-time, which comes from this 40 over here. So our denominator, instead of being 28, is going to be 40. So when we are rewriting our simplified fraction, instead of writing 12 over 40, we are going to write it as 3 over 10. Now let's go on to part C. We have the probability that someone is female given that they're part-time. So let's rewrite this. The probability that someone is female and part-time divided by the probability that someone is part-time. So let's look at where they intersect. We have female and we have part-time. They both intersect at 15. So that means that our top here is going to be 15 where they intersect. Our denominator is part-time. So what is the total number of people that are part-time? Well, that's 31. And 15 over 31, it cannot be simplified. We're just kind of stuck with it like that. So when I'm writing my final answer down, we're just going to write down 15 over 31. What if we flipped it? What if we're asking for the probability that someone is full-time given that they're part-time? Like can we have full-time and part-time at the same time? And the answer is no. If we look here, full-time and part-time never intersect. They are two completely different columns. And while you may have one full-time job and an additional part-time job, that's not what this question is asking. If we're just looking at this chart, can we see where they intersect? And the answer is no. Therefore, we're going to say that the probability is 0.